Hi guys, welcome to my channel. In this video, I'm gonna discuss constant motion related to uh, Newton's laws of motion. Previously, I have already discussed the basic definitions of Newton's laws of motion, and we have done some problems related to Newton's law of motion. So, in this class, I'm gonna discuss constant motion problems related to Newton's laws of motion. So let's start from the beginning. So first motion comes is a rigid body motion, a rigid body system. So what is rigid body system? For example, I consider two blocks and they are connected by a wire which remains tight and they are lying on the ground. For example, the, if the body moves right to velocity a and if it moves right to the velocity b, and I applied condition that this wire, the connecting wire, the wire connecting both the blocks remain taut. It will remain taut. It will never slack. Second condition is massless. I am considering the string connecting between A and B should be massless. And third condition I applied that the wire I considered the wire connecting between them is non-extensible. So in this case, what will happen? If I observe, I will see that VA must be VB. This will happen. This condition must be satisfied. If the wire connecting is satisfies all the three conditions. So let's take a problem. Let's take an example. So if, for example, I am considering a mass pulley system, here I consider two masses here. In this case, I will also assume that first condition will be the pulley is massless, and second condition I will consider that the pulley is non-rotating. Then in this case, if the block moves up, if the block moves up, for example, with velocity VA and it moves with velocity VB, then I can say that VA is VB. They both are equal in magnitude, but in direction wise they are opposite. So, for example, let's take another example. Example 2. The first one was example 1, and the second one is example 2. In this case, I am considering a ladder and a rod is placed in this fashion. So, if I consider that the rod is moving, this end is moving with velocity va, and this end is velocity, the rod is falling down by velocity vb, then for example at certain instant I am considering the angle, this angle as a theta, so I can write, for example, I have to just resolve as it is moving the velocity. I can say that the velocities of each points lying on the this line will be same, because I have considered upward. For example, in the previous case, I considered that the velocity of VA and VB should be same. That means every points lying on this wire, they have same speed or same magnitude of velocity. So I can write, for example, this end it is moving to the left by velocity VA. If I resolve VA, this component will be VA cos theta. Why? Because it is a theta and this should be theta. It is alternate angle, so I will say that this will be a theta. So this is a V cos theta, and in similar fashion, if I draw it, and this will be a pi by 2 minus theta. So it is moving down, so I can say the component of velocity will be VB cos pi by 2 minus theta. As I know from the rigid body concept, that one we have already discussed in the earlier few seconds before. So I will say that each points have velocity, same velocity, but I found here that two velocities. So these velocities should be same. So VA is equal to VB cos pi by 2 minus theta. If I solve this, I will get VA is equal to VB tan theta. And this is the constant relation between V and VB. So I found that the velocities of the ends of the rod are connected by this relation, and this relation is the constraint relation. Let's talk about type of constraint motion. I will discuss few type of constraint motion which are relevant to exams. So first one is the fixed pulley method. Then second one is the moving pulley method. Then third one is the point method. Then fourth one is the wedge constraint. I will discuss wedge constraint in the end. Then fifth one is the I'll constraint of pulley. In pulley method I will discuss step pulley problems. We will discuss these type of constraints one by one. Let's just talk about fixed pulley method. So in case of fixed pulley method, from we can consider that the pulley should be fixed. In the previous example here, I consider that the pulley is not moving, the pulley is at rest. So I can say that the pulley, this problem is nothing but our fixed pulley format. Fixed pulley. So when in this pulley is no longer moving, is no longer fixed. For example, if I consider that this is a pulley and two masses are connected, two masses MA and MB. I'm considering mass of this block as a MA and mass of this block as a MB. This is the block A and this is the block B. And the pulley is itself moving upward with velocity VA. For example, VA, and considering velocities VP, I'm considering this one is a VP and this is a FP. And correspondingly position vector will be XP. Similarly, for this case, I'll consider it is a XB, AB, and VB. These are the position, acceleration, and velocities. Correspondingly, the coordinates for A will be XA, and velocity will be VA, and acceleration will be AB. So They are connected by simple relations xp. It can be seen by seeing this diagram or doing some steps. I will get Xa plus Xb divided by 2. This is the relation, and correspondingly I can find Vp will be Va vector plus Vb vector divided by 2, and acceleration will be Va, sorry, this will be A plus Ab divided by 2. So in this way I can calculate. For example, I'm considering an example. This one, for example, I fixed this one, and I consider this is a mass, and here the pulley is just moving with velocity v. So we have to calculate what is the velocity of m. So from the above relation, I will say that, for example, I am considering it is a va, and this is a vp, and here it is a vb. So vb is 0. So I will say that the vp is equal to va plus vb divided by 2, because b I already fixed it, so vb will be 0. Only pulley is moving up and the mass is moving up. So from the relation here I if I use this relation, then I will find that the pulley velocity of the pulley is twice this one is 0. So velocity of pulley will be the half of the velocity of, sorry, two times, sorry, half times velocity of the mass. So this is the relation between pulley and the mass. Similarly, I can find the oscillations and positions also. Next, go to second step, second problem. I mean, so second problem. This was the first problem related to fixed pulley format. Next, next problem is I am considering this is a wall which always remains fixed. Let me draw the diagram first. So here this is connected in this fashion. Now here is many pulley format. It looks very complicated, but these type of problems are very simple. If we analyze one by one, we don't need to go to the mathematical depth or physical depth of the problem. It seems very complicated, but this problem I will simplify. I can just analyze it what is going on here by simple steps. Don't need to write think many steps. So for example, I'm considering this is pulley A whose mass is capital M, and here pulley B and mass is small m. So for example, this is a pulley, ideal pulley, and for ideal pulley I have already discussed what should be the constraint, what should be the condition for a ideal pulley. So for example, if I displace this if I displace this block by distance x, then it will come here. So this distance is x. Now, as this pulley is fixed, it will not move. So I can say that, for example, I just name this is a pulley P, this is pulley Q, and this is pulley R. So as it moves up, then the wire will also move up by distance x. So it is connected to pulley B, and I know from the constraint rigid body condition, so pulley Q should go down by distance x. So here I will say that as pulley is going down by distance x, and additional thing slack. For example, the pulley Q comes to position. I am considering. mm, Let me draw. For example, I am considering in a, for example, after the slip, after the shift, the pulley Q comes to this position. Pulley comes to this position. So it has already traveled. For example, uh, let me draw. So it comes to in this position and pulley comes to here. So if I see this position, for example, this area from this line to this line should be distance x, and here again in this distance should be x. So I will find if I remove this part, if this x and this x total 2x part, if I remove this 2x part, then the this OR will be remain dot. So I have to, and then I will consider this one as a slack. I will call this slack. How much slack is there? If slack is present, then tension will be zero. Then everything will get complicated. So I don't need any slack. So I have to remove this one. So slack is this one. Next thing is that as it moves up, then another x slack because of this wire will come into picture. Because of this slack, because when it moves up, slack in this wire slack will be x, in this wire slack will be x, and in this wire also slack will be x. So in this case the slack was 2x and additional x will be added to this one because of this wire. So because of this, because of the shift of this wire, the slack is 2x, and because of this wire additional x slack will be present. So the slack in this wire will be, net slack will be 2x, 3x. Total slack will be 3x in this wire. Now consider the same case. So it is moving up. So the total slack is 3x. Is the slack is 3x, then pulley will move down. The pulley will move down by 3x slack. So because of 3x slack, the pulley, if for example I am considering the uh, position of the pulley are here, then additional this slack will come into picture again. So this slack is 3x, and again slack is 3x. So total slack will be 6x plus, because this wire additional x will be also added to it because of this wire. So this wire one is the x. So total x slack will be 7x. So I can write a displacement of x is, or displacement of block 1 as a x, and displacement of xb as a, I am considering the displacement of block A as x, and I found that displacement of xb, displacement of block B is 7x. and correspondingly I can write the velocity of b is equal to 7 times velocity of a. And there obviously the in opposite direction there will be in opposite direction, because here I am seeing that as the block moves up, then block b moves down by 7 times. So this was the all about a moving pulley. Let's talk about step pulley format. Step pulley formats are much more easier than this one. For example, if I consider this is a pulley, bigger one I am considering, and there is another pulley inside pulley, and there is a block. I am connecting this one here. For example, the block this is a mass small m, and here another here is another block where this one I am considering m1 and this is considering m2, and the radius of this one is r and this one is capital R. So if it rotates, for example, it rotates by angle theta. For example, if the mass a1 goes by distance x, so pulley has to also move by distance x rotated. So this will be the arc length. This will be the arc length. So because if this rotation, an angle will be subtended here, theta. So this is same for this pulley also and this pulley also. So I can consider as a theta is equal to length of arc. For example, for bigger pulley, length of arc is x1. For example, I am considering this is a x1. So x1 divided by capital R. For small pulley, for example, it will move distance by x2. I am considering this one as a x2 and this one as a x1. So this will be x2 divided by smaller. So here I can find what will be the x2. So x2 will be smaller divided by capital R x1. So how much displacement will be there I can find. For example, in this case, if it moves up by x1, then x2 will be moves down. X2 will be moved down by distance x2, by distance x2. So x2 is this one. So net slug will be, if I consider net slug, for example, if I erase, I just complicate the situation by making some more pulleys. For example, I am considering here is another pulley. My drawing is very bad, please consider. So it should not be drawn here. So this one is connected to this, and the outer one is connected to this, and there is another block. There is another block connected to here. So I will say that if this block if this block move up by distance x, if the block move up by distance x, then this pulley will also move up by distance x. So because of this, for example, I am considering the current position of the pulley this here. So slack will be present here. So from here to here, center to center, the slack for x and additional here x. So total slack is 2x. 2x. So this distance will be 2x. As it moves up, then this distance will be this 2x. It will be 2x. 2x, and then here, because of as it moves up by distance 2x, then it will also the wire, this one will also go down by distance x2 minus, so and this will be, say, x2 is equal to small r by capital R times 2x. So net displacement will be, will be 2x minus x2, because it is going up, but it is going up by 2 by 2x x, because slack is 2x up, but it is providing a downward slack. It is in opposite direction. It is not moving, so it is also giving a downward slack by x2. So net slack will be, net slack will be 2x times x2. X2 is nothing but small r by capital R divided by 2x. So I will write 2x times small r by capital R. So this is the net slack. Here, if I can consider if capital is R is equal to small r, then there will be no slack. No slack will be present here. No problem. So we already. So this was all about step fully format. Let's talk about wedge constraints. This is, let's talk about wedge constraints. So wedge constraint is nothing but two blocks. For example, I'm considering here, and that this is a one block, and there is another block. For example, this is in this, like, another block. So it is placed on this block, and it is sliding. It is sliding along the surface. So I can see here from there the edge. The two blocks, for example, I'm considering this bigger block has mass small r, small m, and small block has mass small m. So two blocks remains in contact, always in contact. So I can say that as it is moving, so there is no transverse motion of this block. For example, there is no transverse motion. For example, if I consider the relative motion between small m and capital M. So there will be no transverse component. For example, if this is the relative heat to one, the transfer relative velocity, then their transverse component. So their transverse component should be zero, because they are in, they always remain in contact, because there is no, if the block moves along this, it will move along this, not move, it will not detach from the surface, and that will not be so that should be not considered as a wedge constraint. So in this case I will say that the transverse component of the relative velocity should be zero, and also for this relation is also valid for acceleration. So this is the acceleration. Acceleration a12 is nothing but acceleration of 1 with respect to acceleration 2, or in magnitude I can write a12 is equal to a1 square plus a2 square minus 2a1 a2 cos theta. And here I will apply some condition here. This condition, if I apply this condition, then this relation will be simplified to a simple form, because this is the general form, and from the constant relation I will find the I will find the relation between them. So I will put here, then I will find what is a1 and a2. So going to next step. Next problem is, let us talk about is the famous problem. Yeah, this problem is always given in the standard books. If I consider this problem, and there is another block denoting having mass small m, and the bigger block have capital M. I'm I am considering the slash on this is a1 and it is moving along a2. For example, if I fix this one, then this block it will move along this line. So and the bigger block will move along this x-axis, along horizontal axis. So I will write the relative motion a relative. If I consider this one as angle theta, then this will be a1 square plus a2 square plus 2a1 a2 cos pi minus theta. And I have to consider that now what will be the relation between them. A1 if A1 and A2, if I put here, then I will get simple form. So this was all about our constraint motion. In the next video, I will discuss some other problems related to frictions. So see you in the next video. Thank you.